Hello, Math 113. So this is our last section of the course. I know you're so excited. We're going to talk about section 6.6, vectors. So I've got a good picture for you here. You'll see something similar to this later when we do application problems with vectors. So we have two types of quantities. We have scalar quantities and we have vector quantities. And I would like to make a list of each and let's compare. So examples of scalar quantity might be your mom's height. So height is a scalar quantity, or your dog's mass. Notice I didn't say your dog's weight, but your dog's mass. The temperature of your room at any given time, the cost of your new cell phone, gallons of gas to fill up your car. Those are all considered scalar quantities. And I don't want to explain to you what that means. Hang tight while I give you some examples of vector quantities. So a vector quantity might be a drive due north at 55 miles per hour. Now right off the bat, compare that to scalar. What seems to be different? Or if you pull a 50-pound cart up a 20% incline. Are you noticing a pattern here? Or how about you push an 85-pound couch up a 50% incline? 15% incline. 50% sounds like a nightmare. Why would you ever want to do something like that? You know those moving ramps that they have off the back of your rider truck when you're moving? Yeah, you would have to do something like push a piece of furniture up an incline. What else? If you accelerate from 55 miles per hour to 75 miles per hour as you're going south, say driving on 65 to Mobile, that is a vector quantity. Again, are you noticing a pattern of vector quantities compared to scalar quantities? Let me give you, one more. How about 9.8 meters per second squared toward the earth? Anybody know what that is? Do you recognize that? That's gravity. So gravity pulls at 9.8 meters per second squared toward the center of the earth. That is a vector quantity. Now, you probably notice the difference now. Vector quantities have a magnitude along with a direction. So there's a value along with a direction that goes with that value. All of them. So if you're driving due north at 55 miles per hour, 55 miles per hour is your magnitude. The direction is north. If you're pulling a cart up a 20% incline, 50 pounds is your magnitude, 20% incline is your direction. All of these have a magnitude and a direction. Even gravity has a magnitude and direction. And when you take a physics class, which likely many of you will take a physics class because that's why you're in Math 113 to prepare for physics or calculus or both, you're going to discuss vector quantities in much more detail than I do in this section. But there are only 6 vector quantities. Displacement, velocity. I have velocity on the list. That's 55 miles per hour due north as an example. Acceleration, you see I have that on the list too. If you change from 55 miles per hour to 75 miles per hour, you're accelerating, and that's going to be in a particular direction. Force, if you're pulling a 50-pound cart up a 20% incline, that is force. And weight. Notice I didn't say your dog's weight, but your dog's mass. Weight is a vector quantity, and you calculate weight by calculating mass times acceleration. So it involves gravity, and that is a vector quantity. Okay. On the other hand, a scalar quantity involves magnitude only. So your mom's height, your dog's mass, the temperature of your room, the cost of your cell phone, how much gas you put in your car. All those are singular scalar quantities. You don't need a direction to go with that. Okay, so now you know the difference between scalar quantities and vector quantities. Now let's get into the thick of the lecture. A line segment to which a direction has been assigned is called a directed line segment. Fancy name, right? So it's the line segment. Remember, line segments have a beginning and an end. And then if you put a direction to it, it's called a directed line segment. We denote this directed line segment by noticing, let me get my pen working. Stand by just a second. So notice the notation here. It bothers me just a little bit. I don't know if you remember from geometry, but when you have a line like that, we call that a ray. Well, in this instance, it's a directed line segment. A ray is really half a line. So it has a beginning but no ending because it goes on forever. That is not the case with this notation. So if you see it in this section, that is called a directed line segment. So you see a line segment with a beginning and an end. The arrow is only to indicate which direction it's going. And it does matter if the arrow is on this end, which it is in this case, or if it happened to be on the other end down here at P. Those are two different directions, okay? So the magnitude of the directed line segment PQ is called its length. So if you see this notation, so you see, first of all, PQ with the line with the arrow over it is the name of the directed line segment. Those vertical bars, double vertical bars, looks like absolute value gone wild, right? So 2 bars on the left, 2 bars on the right. That means the magnitude of the directed line segment. And geometrically, a vector is a directed line segment. They are the same thing, okay? All right, now a little bit about notation. So in print, in a textbook, in my PowerPoint representation, you're going to notice a vector, we use bold. So if you see a bold V, that represents a vector, or a bold W. But on paper, we can't bold, right? So how do you handle that? So it would be V with that directed line segment over it. So that's how you represent a vector on paper. Or W with the line over it. Okay, now in print, if you want to represent magnitude, remember the vertical bar's gone wild here, so double absolute values V, but if you need to do that on paper, you got a lot to write. So you have V with the line over it because we can't bold with the vertical bars, or W with the line over it and vertical bars. So the line over the top, the directed line segment, means you have a vector, and then the vertical bars means the magnitude of that vector. Okay, now the next thing I want to get into is how do you know if vectors are equal? Okay, so in general, vectors V and W are equal. They are the same vector if they have the same magnitude and the same direction. That's going to be very important to some homework problems. Okay, same magnitude, let me highlight same over here too, and the same direction. Well, of course, right? Because a vector has both magnitude and direction. Well, the only way V is going to equal W is if they have the same of both of those things, magnitude and direction. I've got some examples below. Example A, V does equal W. Notice they are the same length. That's really what you're looking at when you're thinking about magnitude, is the length of this directed line segment. And V appears to be the same length as W. Not only that, they're pointing in the same direction. So V is equal to W. Now check out B. V and W have the same length, which really means they have the same magnitude. So make sure you use the right vocabulary. The length of a vector, or the value of the vector, remember, it has two things, magnitude and direction. And so magnitude really is the length of the vector. We'll talk about more in a minute, but these aren't pointing in the same direction. So V and W are not equal in this case. So vector V is not equal to vector W. Now you could say this though, vector V magnitude-wise is equal to vector W magnitude-wise. Look at C. What's going on there? They look like they're pointing in the same direction. Kinda. But they're not, are they? One is going downward, and then one seems to be going up and towards the left. But they do appear to be the same length, which would mean they have the same magnitude. So here, just like on B, we do have the same magnitude, but we definitely do not have the same direction. So these vectors are not equal on example C. And example D, notice they are pointing in the same direction, so we could say they have the same direction, but W is definitely longer than V, so these are not equal. So the only two that are actually equal here is example A. They have both the same magnitude and direction. All right, now we have a first problem. So we're supposed to show on this problem that vectors U and V are equal. If they are actually equal, who knows? But we have to show it. Now, when I look at them on the graph here, They appear sort of to be equal, right? They look kind of like they're pointing in the same direction. But how do we really know? You know, in math, you're not supposed to just look at something and go, yeah, it looks right. Right? You're supposed to prove it. Same thing with the length or the magnitude of these vectors. So there's two things we got to show, right? We've got to show that these two vectors have the same magnitude and these two vectors have the same direction, okay? Now remember, magnitude is length. Any ideas how to find the length of these vectors? Well, let's go with the vector on the left. That is called u. Okay, so I want to find the magnitude of u. Let's use proper notation. There we go. That's the magnitude of u. How am I going to do that? Do you not know? Yes, you do. The distance formula, right? The distance formula is, let me go ahead and write the formula down here. So x2 minus x1 squared plus y2 minus y1 squared. You've seen it. You saw it in your pre-calculus algebra class. You have seen it in your trigonometry class at different times. So if I subtract my x values, okay, -2 minus a -5, y'all be super careful. Please be super careful with your signs when you do that. So that is a -2 x value minus a -5 x value. Okay, subtract my y values. That's 6 minus 2 squared. Okay, now where's this distance formula coming from? Remember the Pythagorean theorem. So -2 minus a -5 is 3. 3 squared is 9. Notice I'm leaving out some steps. I need some space. 6 minus 2 is 4. 4 squared is 16. Okay, looking good. Square root of 25. Don't forget to take the square root. That is 5. Now I've also have to find the magnitude of the vector v. Again, notice the notation. Those vertical bars, double vertical bars out there being magnitude, which is really the length. I forgot my square root bar. Here we go. All right, I'm going to subtract my x value. So that's 5 minus 2. Don't forget to square it. Plus, subtract my y values. That's 6 minus 2. Once again, don't forget to square it. So that's the square root of 5 minus 2 is 3. Then 3 squared is 9. Plus 6 minus 2 is 4. 4 squared is 16. We are looking like matches, right? All right, so we have shown that the magnitude is exactly the same for these two vectors. Doesn't that mean they're equal? No, we still have to show that the direction is the same. And it's not going to fit on this page, so hang tight while I flip over. All right, so how are we going to show that these directions are the same? Any fancy ideas? How about way back in several of your algebra classes? Direction of these lines. How do you measure direction when you're dealing with an XY axis? Remember, straight lines have a slope? Hey, yeah, that's one way to do it. Why don't we find the slope of each of these line segments or directed line segments? So remember the slope formula. Maybe you don't. Slope m is y2 minus y1 divided by x2 minus x1. Y'all know that is rise over run. So if I find the slope of vector u, and that's really vector u, let's use proper notation, we would have y2 minus y1, so that's 6 minus 2, divided by x2 minus x1, so that's going to be -2 minus a -5. Now be careful what you set up as your 1s and your 2s. I said this was my 2 and this was my 1. You got to be organized about that. So 6 minus 2 is 4, and -2 minus a -5 is 3. So my slope for u is 4/3. Okay? Also have to find my slope for vector v. All right, so here we go. y2 minus y1, so there's my 2's, 6 minus 2 for my y values, over my x's, my bad, 5 minus 2. 6 minus 2 is 4, over 5 minus 2 is 3. Look at there. We have the same direction. And slope is probably the easiest way to calculate the direction of a vector as long as it's in an xy axis and you have that in point form. So we did it. We proved that they have the same magnitude and the same direction. If the magnitude were to be different or the direction were to be different, then these vectors would not be equal. You have to show both. Now let's spend a little bit of time talking about vector operations, like what can you do with vectors, and what do I mean by operations, like multiplication, addition, subtraction, that sort of thing. What can we do? Well, one of the things we are allowed to do is called scalar multiplication. Remember what scalar meant earlier? That's just a magnitude. There is no direction. And you are allowed to do scalar multiplication with a vector. You take a scalar, just some number, times a vector. Okay? Now in this case, we're going to call the scalar k. And I thought I picked out a highlighter. There we go. Scalar k times the vector v. And the product, you just do kv. Again, notice the v is bold because it's a vector. If we were to write that on paper, it would look like this, kv. Okay? My arrow is looking a little bit wild. Let me. It's hard on this squirrely computer screen. That's kind of better. kv. Anyway, so multiplying a vector by any positive real number, except one, changes the magnitude. So check this out. We've got vector v right here. Here's v. All right. Two of those, what does it do? It just doubles the length. Notice the direction is exactly the same. On the other hand, 1/2 v is half as long as v over here. Not half as long as 2v. Remember, we're going back to b. So half of v looks like this. The best one is this last one down here. I'm going to highlight in some kind of orangey color. Look, -3/2 times v. Excuse me. So 3/2 we know is 1/2. So this is 1/2 times the length of v. But look, it's pointing in the opposite direction. I know it's hard to see, but that arrow is down here instead of up at the top. Why did that happen? Because we multiplied by a negative, right? A negative number, when you multiply a negative scalar times a vector, it reverses the direction of the vector. It makes it point in the opposite direction. Cool, right? All right, so more about scalar multiplication. If k is a real number and v is a vector, the vector k times v is called a scalar multiple of the vector v. The magnitude and direction of kv are given as follows. So, get my pen going again. All right, so notice to find the magnitude, you just take the absolute value of your scalar k and the length of your vector v and multiply those together. Okay, so the absolute value of k times the magnitude, which is the length of the vector v. Then kv has a direction that is the same direction as v, as long as k is greater than 0, and the opposite direction of v as long as k is less than 0. Remember, that was our orange highlighted right here, opposite direction, because we multiplied by a negative. All right. More. There's more. What if we want to add two vectors together? Okay, so when you take a physics class, and you may even do this in your calculus class, but definitely when you take a physics class, you're going to add vectors and find what's called the resultant vector. That's the answer of two vectors added together. Okay, now it says the geometric method for adding two vectors is shown in the figure. So when you look right here, we're adding u plus v. So how do you do that? Well, you start with u. Notice u has, again, a particular length called the magnitude and a direction. And this is like the tail to tip method. You plop v right at the end of u. Okay? And the vector that starts where you began and ends where you left off is called the resultant vector. I had to do this a lot in a physics class. I'm actually in multiple physics classes and other classes as well. I anticipate that you're going to have to do this, and you probably already have. If you took high school physics, likely you did that in there. In this section, we're not going to do the tail to tip method. We're going to make it way easier. So, whew, yay, right? But I want you to realize when we add vectors together, this is, think geometrically, this is what's happening. You start with a direction and a magnitude, and the second one you start at the tip right there and draw the other vector, and the resultant vector really starts at where you began and ends where you left off. Okay? And that's called u plus v. But we're not going to do it that way. What about subtraction? Whew, what would that look like geometrically? Now, this picture, when you first look at it, is kind of a mess, all right? What we're doing here is v minus u. So we're starting with v, and we're subtracting u, okay? Now, where's v in this picture? I'm going to highlight her for you. There's v right there, okay? And it shows U down here at the bottom. Okay, so that's just what V and U look like. Now, what I'm supposed to do, remember, if I do that tail to tip situation, which you're not going to have to do that in the homework, don't stress, but I'm going to take U, right here it is, and if I were to add it, I would pick it up, here it is, and put it right here. Okay, same direction, same magnitude. And the resultant, y'all, I'm going to erase this in a minute, would be this dude right here. That's U plus V. Now, we're not doing U plus V, right? We're doing U minus V. All right, so let me get rid of all my tricks here. Now, to do U minus V, I'm supposed to pick up U, put it at the tip of V, but I'm doing minus U. So I've got to draw it backwards. So that's why it's backwards like this. And again, my resultant vector in red is that guy right there. Okay? That's my resultant vector of V minus U. That means you start with V, and then you do a negative U at the tip, and there you go. I hope that makes sense. Again, you don't have to do that way in the homework. There is a much easier way to handle it, but warning, you're probably going to have to do this in a physics class at some point. All right, now I'm going to introduce you to something called the I and J unit vectors. I promise I'm going to get back to a problem eventually. We've only done one so far. It's a whole lot of definition. But the I and J unit vector. Okay, first of all, a little bothered by this. Now, I used PowerPoint presentations from our textbook. Matter of fact, at the end of this presentation, I'm going to show you the copyright screen because I did copy straight up. But we are using the textbook. I've paid my fees. You've paid your fees. And so it is okay that I use their PowerPoint presentations because it was much easier than building my own diagrams. But one thing that bothered me is they introduced this notation right here, unit vector. But they haven't defined it, and they don't define it until much later on. But let me tell you what a unit vector is. A unit vector has magnitude of 1. You remember anytime you see unit, like unit circle, it means it has a radius of 1. Well, a unit vector has magnitude of 1. So anytime you see that term, that just means that that vector is 1 unit long. Okay, whatever units you're speaking of. Now, notice this. We have the I unit vector along the x-axis, and it's only 1 unit long. And then we have the J unit vector right here along the y-axis. It is also 1 unit long. Okay, why is that important? Because we can write any vector using I and J notation. Wait for it, here it comes. Okay, so the vector V that starts at 0, 0 and goes out to AB. So look at this picture over here at the right. This vector started at 0, 0. I'm going to highlight it in green for you. Started at 0, 0, and it just goes out here to AB. All right? It can be written as AI plus BJ. Now remember, A is going to be the distance here along the x-axis times the unit vector that goes along the x-axis. So I is always the unit vector along the x-axis. So A is like a scalar. It's just the length times this unit vector along here. Whereas BJ, okay, J is the unit vector along the y-axis, which is 1 unit long. And if we multiply that times the scalar B, it's going to be the length we need. Now, this might sound complicated right this minute. Really, it's not, okay? So when we start working problems, this is going to be really easy. You're going to feel really solid about it. So A is called the horizontal component of V, and B is called the vertical component of V. And remember, I is horizontal and J is vertical. And they say the vector sum, AI plus BJ, is called a linear combination. So here's your term, linear combination of the vectors I and J. And then the magnitude, okay, remember the magnitude is the length, right? So earlier we found magnitude by using the distance formula. Here it's showing us magnitude using, what is that? Yeah, that's the Pythagorean theorem, which y'all, the distance formula is nothing but the Pythagorean theorem anyway. So it's A squared. Remember, A is across the bottom, so it's A squared plus B squared over here is equal to my C squared right there, okay? You've done this a lot already in this tree class, right? So this, no problem. We've got this. Okay, you're going to think this is easy peasy. Example B, finally. Sketch the vector V. Notice the bold V because it's typed. If I was writing it on paper, it's going to look, come on now, like that. And I don't care if you do that fancy V with a little kick at the end or not, but there's a V with a directed line segment across it. That means vector V. Okay? And they want us to sketch it. Sure, we can do that. Remember, negative 2i plus 4j. The negative 2i, remember, I is a unit vector in the horizontal direction, whereas j is the unit vector in the vertical direction. So we need to go negative 2 in the horizontal direction. So negative 2 is out this way, right? So here's negative 2. And then 4 in the vertical direction, that takes me right here. But it's just like plotting a point. So there's negative 2, 4. And my vector, y'all forgive me, it's not going to be straight because I cannot graph a straight line on this squirrely pad. But yours is going to look awesomely straight. If I could use a ruler without marking all up the screen, then I would do it, but I can't. I could use the straight line tool, but that might be more, I don't want to get into all that. You see how to do it, right? You just go to negative 2, 4, just like plotting a point, and that gives you your vector in like a standard position because you're starting at 0, 0. And then you end at negative 2, 4. It's easy, right? It's easy. Now, we're supposed to find the magnitude also. So remember, this is the point, negative 2, 4. Might want to label it, help you remember what's going on here. Magnitude, you need those double vertical bars, or the wild-looking absolute value. And remember, it's the Pythagorean theorem. So it's going to be a squared, so negative 2 squared, plus b squared, 4 squared. Did you notice I didn't put in the I and the j? You don't, right? So no i's and j's, no vectors go into this calculation. It is, just the components, the negative 2 and the 4. So negative 2 squared, of course, is 4, plus 4 squared is 16. That gives me the square root of 20, and then we get to use our awesome reducing radical skills that you have to do so much in this class. That's going to be the square root of 4 times 5, right? Because 4 is the biggest perfect square that divides into 20. Which simplifies to 2 times the square root of 5. And that is what we call the magnitude, notation-wise, wild vertical bars. There you go. Okay, so in standard form, sketching the vector, and we have the magnitude is 2 times the square root of 5. Hey, be careful in the homework. Sometimes they want the magnitude in actual value like that, and sometimes they like it rounded. And that's where I always make my mistakes because I don't read directions thoroughly. So make sure you read the directions thoroughly in your homework. What if we need to represent vectors in rectangular coordinates? What if it's not like, well, let me just hush. Okay, if you have a vector v with initial point x1, y1, and terminal point x2, y2. Okay, so what am I saying to you here? Let me graph. Okay, so here we go. Here's our xy axis looking awesome, and our initial point right here is x1, y1, and our terminal point, let's just say it's over here, is x2, y2, and there's my vector. Okay. I can't write that in IJ form because this guy right here is not parked at the origin. It's not really in this standard form where you start at 0, 0. So how do you fix that? Hey, it's a real easy fix. You just do x2 minus x1. You subtract the x's, and you do y2 minus y1, and you subtract the y's. Now, most of the time in math, it doesn't matter which you label x1, y1, or x2, y2. This is when I'm talking about calculating distance or when I talk about calculating slope. As long as you're consistent, like label it and keep it that way. But for vectors, it matters a lot, okay? It changes the direction. Your x2, y2 must be the direction. So it begins at x1, y1. That's why they call that the initial point. And it ends at x2, y2, and that's called the terminal point, okay? So just be sure to subtract them in the proper order. So let's do an example C. Let V be the vector from the initial point, P1, to negative 5, okay? So I'm going to plot that point to negative 5. So I go over 2 and down to negative 5. That is, why am I not working here? That is my P1, 2, negative 5, okay? And then my terminal point, this is where the vector ends. P2 is negative 6, 6. So negative 6 along the x-axis, positive 6 along the y-axis. There he is right there. So negative 6, 6. And then please don't laugh at my line. It starts here and it ends there. And the slower I draw it, the worse it is. I got slow right there in the middle, so it's got a hump. Notice again, terminal is where you draw the arrow. That's my vector. But the problem is I can't write it in terms of I and j because this initial point is not right here at the origin. So how do we fix that? We use that cute little formula I gave you a minute ago. x2 minus x1i plus y2 minus y1j. I subtract my x's and I subtract my y's. So I'm going to write the formula here because you know how you learn formulas. You write them down every time you use them. Okay, so x2 minus x1. So does it matter the order I subtract? You bet it does. You have to do the terminal end first. Negative 6 minus 2 I plus, again, terminal end on the y's too. 6 minus a negative 5 j. What's my only concern? Signs, of course. So negative 6 minus 2 is negative 8 I. 6 minus a negative 5 is going to be plus 11, be careful, j. Now, let's plot that. Let's see if it looks like the same vector, okay, just in a different location. So if I go to negative 8 and then 11, which actually doesn't fit on my graph, but we're going to put it there anyway. So negative 8, 11, and I draw it up. That line looks a little better, doesn't it? Would you agree that appears, and remember in math that's not really fair, but if it looks right after you've done the calculation, that's okay. Does it look about the same length? Sure it does. Does it look like it's in the same direction? You bet. Okay, that's not a proof, but that is a kind of a backup to our work. Now, easy so far, right? I've already hit the 32-minute mark, so I want you to come back for part 2. You could probably get a very little bit of the homework done with this much of the lecture for part 2, and there may be even a part 3 because some of these application problems take a long time. And we'll talk about adding vectors and subtracting vectors, not using the tail to tip method where you find the resultant, but using the much easier method. Okay, so come on back and we'll finish this sucker up. Have a great day.